Hey crew, this will be the video for exercise 11C, transition matrices using recursion. So we want to be able to use a matrix recurrence relation. So we start off with an initial matrix called the initial state matrix, and we're going to be using the recursion template to get the next term, your previous term, and multiply by a transition matrix. And that will generate a sequence of state matrices. And you want to be able to informally identify a thing called the equilibrium state or steady state matrix. And this is using ways to essentially predict the future through repetitive matrix multiplication using a rule. So let's construct a matrix using recurrence relation. And what this actually means is, let's say that in the previous exercises that we've been looking into, there's always like some starting point or some type of reference number. So let's take the example of the car dealership. There was a certain amount of number that it starts off with, and then over time we want to see what happens maybe in the next week. So like 10% of cars go to this place, 20% of cars goes to another place, and then the remaining 70% stay or returns back to the same spot. Now, but because this is going to be happening multiple times, we will create what's called an initial state matrix, and this is always dictated by S of 0 being the initial, and the list of the amounts always stacks vertically. So let's say this could be the example of the amount of cars starting in two places, Bendigo and Colac. So we can dictate this by the letter B and the letter C by the starting point. To find out the next number of cars, so to generate S of 1, after 1 week, time frame in this case is weeks, we're going to use this particular transition matrix. So 80% if it starts at B and returns back to B, so it starts at Bendigo, returns back to Bendigo, 80% is going to return there. The other 20% will go to Colac. And then vice versa, if it starts at Colac and it's going to go to Bendigo, only 10%. But if it starts at Colac and returns to Colac, this will be 90%. And this is how the transition matrix is being set up, just arbitrary numbers maybe from data. So to get your next S, you're going to get your transition matrix and multiply it by the initial. So kind of like recurrence in finance, we're doing effectively the same thing, but we're doing this with matrices now. So remember, with matrix multiplication, it's always you get the first across and attach it to the first and only column down. So 0.8 times 50, 0.1 times 40, and then add the two together. We'll do this again within 0.2 and 0.9. And you'll notice that when you stack these up, this should equal 1, and this should equal 1, because this accounts for the 80% and the 20% of what's happening to the 50 that makes up the 100%, and then again the 10% and the 90% that makes up 40, which again adds up to the 100%. After 1 week, we will see that 44 cars will then be in Bendigo and 46 cars will be in Colac. Now you can do this again and again and again, because you can use this as a recurrence, just like in finance. So S2, same thing, get your transition matrix. This stays locked in. Okay, so this is locked in. It's these values here requires you to refer to the previous one. So that was 44, 46 we just worked out. After another week, we end up at 39.8 and 50.2. And then we do this again, and this keeps going. Now eventually it does hit like a steady state or equilibrium. One doesn't just shoot up to 90, the other one goes to 0. It will hit an equilibrium point, but we'll see this as we go later down the track. So in general terms, to get your next term, n plus 1, you just get your S of n and multiply it by t. You always have to do the transition matrix multiplied by the actual previous matrix. Okay, order does make a difference in this case. And there is an image of Keanu Reeves. Okay. All right, so we're going to be looking into this example here. The factory has a large number of machines. The machines are going to be in one or two states. It's either operating or it's broken. Broken machines are repaired and come back into operation, and the other way around. So a machine can start off fine and then it can break. At the start, 80 machines are operating and 20 machines are broken. And we're going to use this recursion relation to find out what the likelihood of, just as a prediction, what will happen the next week, next day in this case. Now, this transition matrix, if you wanted to interpret this, if you start off with machines that are operating, so this is operating and broken. If it starts off operating, the next week, 85% of them are going to remain operating, and then the other 15% will be broken. And then from the broken ones, the likelihood of them being able to be operating the next week is a 5% chance, but then 95% of them will remain broken. Probably not the best model for this particular work. But this is just the transition matrix. We're going to determine the number of operational and broken machines after 1 and 3 days using recurrence relation. So to set this up, remember to get S of 1, this is the transition matrix multiplied by the initial. So in other words, if we have our transition matrix here, so that was again 0.85. Now you can use your calculator to store this as transition matrix T, and you can just go ahead and use that to do the multiplication. We start off with 80 and 20. Remember, that's our operational and our broken. When we go ahead and do this multiplication, row times down, row times down, you'll end up getting 69 and 31. So this is how many will be operational, and this is how many will be broken. So they'll be looking like it's going to be less operational and more broken. So that's S of 1. Now, just like any recurrence, to get your S of 2, you get your transition matrix and you multiply this by the previous one. So again, this stays locked in, 0.85, 0.15, 0.05, and 0.95. We're now going to multiply this by 69 and 31. So that came from S of 1 here. When you put this into your calculator, you will get 60.2 and 39.8. Now the question is requiring to get S of 3. So we do this again. S of 3 is equal to transition times S of 2. When you do this successfully, this stays the same. That gets put into your calculator and you will end up getting 53.16 and 46.84. Now remember, these are just predictions, okay? These are just predictions, but this is just based on data that's used to model if this is going to be consistent, this is going to be a result on a day-to-day basis. Now, we can also put this in the terms of a rule, okay? Just like within finance, if you know that this is going to be recurrence, to get the rule, to get any time frame, whether it's day, month, year, whatever the context of the question is, you get that transition matrix and you put it to the power of whatever that time frame is and multiply it by your initial amount. So because that will take the transition matrix again and again and again and again, and we'll keep doing it to the initial. So for instance, let's take that same factory, take that same transition, take the same initial state of 80 and 20. What's going to happen after 10 days? Well, once you store these two, you put the transition to the matrix of 10. After 10 days, it's going to hit 31 and 69. Okay, so 31 operational and 60, approximately 69 broken. And this rule is really cool because this can then also help you to dictate whether there's going to be some type of steady state or equilibrium that happens over time. Now, of course, if we can go forwards, we can also backtrack as well. And we do this through inverse matrix. So if we've given a particular recurrence relation, if we want to get the one before it, we take the one that we have after it and do a pre-multiplication by the transition inverse. And we know how to find an inverse using our calculator. We can just put it to the power of -1. So in this particular example, let's say we have a transition matrix and we have got S of 4, and we want to figure out what S of 3 and S of 2 are. So to get S of 3, since we know S of 4 is this, to get S of 3, we take the transition matrix, put it to the power of -1, and times that by S of 4. Now, just for the first one, I'm just going to write out what this transition matrix is. So remember, you put this, you store this into your calc, and then you just literally put t to the power of -1. Now, there's different ways that it could be represented. This is what it will be. If you remember, transition matrix times the inverse of it will give you 1, 0, 0, 1. We use this as a bit of a hack to figure out this. So S of 3 is this matrix here, multiplied by this matrix here, which is S of 4. 2, 5, 5, 8, 7, and 3, 4, 4, 1, 3. When you do this correctly, you will get 25290 and 34710. So here we have got our S3. We do this again to get S2, multiply this by this to get S2. S2 in this case will end up being 24300 and 35700 when executing this particular multiplication. Remember, S3 just came from there. Now, the steady state solution, what we can do is, if we just do small week or month or whatever time frame iterations, it will come up with an incremental change. But over time, if you do this again and again and again with high n values here, you can see that there's barely any change. Okay, so what actually happens is it hits this nice equilibrium state. Now, if we're taking this Bendigo-Colac example, the cars are moving, okay? So when cars are getting hired out, some cars are returned back to Bendigo and or goes to Colac and vice versa. It doesn't necessarily mean that nothing's happening. Action is happening, but it balances itself out. Okay, so this is state number 1. And state number 2, for this particular system to have a steady state, the transition matrix that you create has to be regular and the columns must add up to 1. So there can't be any discrepancies with the percentages that gets distributed. A regular matrix is one whose power never contains any 0 elements as well. You can't just have 0% of something that happens, because then that's not really going to hit a equilibrium state. It'd be pretty weird or kind of fluctuate if that were to happen. In practical terms, this means that every state represented in the transition matrix is accessible either directly or indirectly from any other state. So there has to be a way from one car to go to another place or to its own place. And if this happens with different places, so maybe you might have 4 different stations, every single car place has to have access to the other 3, okay? And none of them can be represented with the 0. For that to happen, you will get an equilibrium or steady state. And how you just work that out is you try to figure out what the term, like say you want to work out what the steady state is, you work out like S of 120. So you do something like this and multiply it by its initial or some ridiculously large value. And just to cover your N, you can do something like that. Work out S of 120 and S of 121. See if there's any difference between the two. If there isn't, you know you've reached your equilibrium. All right, and here are the questions. 11C, page 567, 1, 4CD, 5, 6, 4, 7. Have fun with the exercise 11C. Enjoy your holidays. Catch up.